about the phase change, the temperature change, a phase change, and also when you have a temperature change in the problem. Basically, all of these problems about heat can combine these two right here. So it's written out a few different ways, kind of as different statements on the objectives. Number 11, number 12, and number 15 are all about using these cues right here. On number 12, where it says to apply the method of mixtures to solve a calorimetry problem, the method of mixtures is basically what we've been doing here, just putting them all together. There's no special method to that. There's nothing else I need to say about that. It's all about using these cues. So just kind of make a note that all three of those are basically about using these two equations for Q's. The phase change and the temperature change equations for heat energy here. Okay. 14 was about that phase diagram, which we will need to draw sometimes just for ourselves. When we're doing problems with the phase change, that might be useful. And then number 13, it says apply the law of conservation of energy to determine the change in temperature when mechanical work is done. That's like the one I was talking about where we drop a stone into a pond and it heats up, or let an asteroid hit a lake or something or the ocean and see what that does to the temperature of the water. Okay. So let's do another one now where we're going to have both a temperature and a phase change. So if we look at number 3 now, we've got some ice, which is initially at 0 degrees Celsius, added to 0.75 liters of unsweetened tea at 20 degrees Celsius. We want to make the coldest possible iced tea. If enough ice is added to the final mixture so that it's all liquid, we want to know how much liquid's in the pitcher when that condition occurs. So when it becomes all liquid. So basically here we've got a container of liquid again. Okay. This is tea, or it's unsweetened, so it's just basically the same thing as water. We don't have all that sugar in there, so the density here, the specific heat, this will all be just basically that of fresh water. We have 0.75 liters to begin with. We're going to take some ice and just put it into the container there. We're going to talk here about just the energy transfer between the iced tea and the ice cubes and not the container. So we're assuming here that there's no energy lost or absorbed to the container, the pitcher right here. This could be a big styrofoam cup or something, but we're not doing any energy transfer to the surroundings or to the container. This all initially right now is just between the ice and the tea or the water. Okay? So we've got this case here, putting that in there. Eventually the ice will go in there, it's going to melt completely. We're going to have a container full of tea or just water basically at the end. We want to know how much is going to be in there. How much ice do I need to put in there to make the coldest possible tea and let it all melt. Okay. So let's start writing some things down. We're basically going to have the water and we're going to have the ice. This is our tea. And let's start writing some things down. Now, we should always be thinking about what kinds of heat we're going to have. What forms of heat do we have here? For the water or the tea, what kind of heat transfer do we have there? Phase change, temperature change, or both for the tea, the water that we have? Temperature change. So we should be thinking about writing things down for the M, and I'll just choose this to be my 1, I'll choose this to be my 2. We're going to have M1, we're going to have C1, T01, T1, maybe we'll write down the delta T1 also. Okay. We don't know its mass, but we do know we have 0.75 liters of that. What's a liter a measure of? So let's call this a volume for 1 right now, now that we chose the 1 for the T there. Okay? Do we know the initial temperature of the water?
Yes, 20.
Okay, so this is at 20 degrees Celsius there, so we can write that in here. The specific heat, do we know? Yeah, 4186 joules per kilogram per degree Celsius there. Okay. Can we get the mass of the water? How? We know the volume of it. We know the density of it, so the density is equal to 1,000 kilograms per cubic meter. 1 liter is equal to how many meters cubed? Anybody remember that?
What's the question?
1 liter is 10 to the minus 3 cubic meters. That's a conversion you could look up in your book. That's probably in there in the front cover also for your volumes or somewhere up there. But yeah, if we know that conversion from liters to cubic meters, we know the density, we know the volume, we should be able to solve for the mass. And really, what we're going to see, because this is fresh water, which is 1,000, and because the liter is 10 to the minus 3 cubic meters, we can say that 1 liter of water is equal to 1 kilogram of mass. Because of these numbers here. That doesn't work for everything. If you were going to solve here, you would just say density is equal to mass over volume. So 1,000 kilograms per cubic meter times your volume of 0.75 liters. But then change that to 10 to the minus 3 cubic meters per liter. That would give you a mass, which is left over in kilograms. But this is 1 over 1,000, that's 1,000, right? That's how you see it's a 1-to-1 conversion when it's water. 1 kilogram of water is equal to 1 liter. Okay. Only because of these numbers here that we have, with this being 1,000. Okay. But you can plug it all in if you want to and see that we'll get 0.75 kilograms of water would be the mass of 0.75 liters. These liters cancel out, cubic meters cancel out, and then these 1,000s cancel out also. Okay. So that's a quick conversion that you might remember, that 1 liter of water is 1 kilogram of mass, but it's not one that you wouldn't be able to figure out if you knew the density. Okay. So we know all that. Do we know the final temperature? Let's come back to that now. What about ice? What do we have for the ice here? What kinds of Q do we have for the ice? We have a phase change. We have a temperature change. This is where I say draw the phase diagram. And just a quick sketch just showing these diagrams can be very useful. We know that for water, what's this number right here? And then up here? For the melting and the boiling points of water in degrees Celsius there. Okay? Where are we on the phase diagram to start with? All the way at the bottom? For our situation, we have ice at what temperature? So our ice is at 0 degrees Celsius when we plug it in there. So we're starting right here on the graph. If this ice was anything below 0, we would be down here. And we would have a temperature change there before I could change the phase and melt that ice. Okay? So we know we're going to have this part, but do we know how much of the ice we melt? You know, I think we do here because it says we're going to melt all of it. At the end, it's all liquid. Right? So we do know that we melt all the ice. We don't always know for sure if we can melt all the ice around. It depends on how much energy we have to be able to give to it. But here it said that we want to melt all the ice. Okay. So we're going to do this part here with the Q. And this Q right there is equal to M times LF. And then we need to kind of ask ourselves, do we have any piece here or any piece up here? We know we don't have anything down here because we start at 0. Now we need to determine what our final temperature is going to be. So let's just first start with mass 2, which we don't know. The latent heat of fusion we can look up in the table. So you'll see that there for water to be 3.33 times 10 to the 5th joules per kilogram there. Our final mixture is all liquid because it said here that it was in the problem. So we know we've melted all the ice because of this statement right here. We want the coldest possible T. Any ideas what that would be?
V1, unless you wanted to anchor it down to the decimal. Shouldn't it?
And so if it's cold as possible, we could be down as low as what?
Just above freeze, like 0.
Just above 0, or basically at 0. So our coldest possible T is at 0. When it's there, and we can add as much ice as we want to get there. So let's say it's all liquid at 0 degrees Celsius. That's the coldest possible T. So that tells me that my final T here is at 0. If we're going to end up at 0, that means all of the energy went into melting the ice, but then we didn't raise the temperature after that. We can stay there at 0 if we get all that ice in there and melt it all. Okay? So there is no temperature change here also. We're going to do one later where you're going to have to account for more than one part on the phase diagram. But here, because we want the coldest T, we're just going to melt all that ice. It started at the melting point, so we only have just the 1 Q for that. Okay. Is that clear? James? Doesn't look clear.
I would think we would start to freeze it again at 0. We'd be turning back into someone.
That it would be going back this way, but then at that point you have to remove energy from it. So if there's if there's no more energy to be able to remove from it, you can only remove energy if you are at a lower temperature. And so you have to be trying to go back down into this region down over here, and you're not at a lower temperature, you're not in the freezer, so it doesn't want to go back down that way. There's nothing to take the energy away. That energy would have to go away from the ice into the colder room to heat up the colder room, or to heat up, what's really happening is we're heating up the freezer by taking energy away from the ice. But we don't have that here because we're not at a temperature that's below 0. So it won't just go back and forth. It's trying to go either this way or this way, depending on the temperature. There is no temperature change during the phase change, but it's trying to go in whichever direction the temperature of the surroundings is. Okay. So yeah, that's it for our Q's. We are always going to conserve energy and say that the sum of the Q is equal to 0. For this isolated system, we're conserving energy. Now there might be and there will be energy lost sometimes or absorbed by something else. You know, we're focusing in on just this right here. But then there's the temperature of the room might be something different. Eventually this is going to warm back up to room temperature. But we're not looking at anything else other than just the water and the ice right now. We have just those two Q's, the Q1 and the Q2. Now with the Q2, we have to choose the sign of that Q2 on our own. What sign would that be? Which way are we going on the phase diagram? Left or right? We're going this way in the direction of positive, increasing Q, that's plus. So just make sure you're thinking about that if you're going the other way. So now we really can just plug in our M1, C1, delta T1 plus M2, LF is equal to 0. We're trying to solve for mass 2, so let's just rearrange here and get M1, C1, delta T1 over the latent heat of fusion. This is equal to mass 2. I'll put a minus sign out in front of that because we had to rearrange the equation to get there. So just subtract over the MC delta T and divide by the latent heat there, and we'll get the mass. And we've got numbers for all these things over here. The M1 is the 0.75 kilograms, 4186 joules per kilogram per degree Celsius. Our temperature change, we didn't write down, but what is it?
-20.
Yeah, -20 here because we were going from 20 down to 0 for that iced tea. And the latent heat of fusion denominator here is 3.33 times 10 to the 5th. So these two minuses cancel out, which is good. We need a positive mass here. This is our mass 2. Plug all these things in, and we'll get 0.19 kilograms for mass 2. Did that answer the question? What's the question asking us for?
How much liquid?
How much liquid's in the container at the end, so how do we find that?
Add the 0.75 and
This is just equal to 0.19 liters of water because of that one-to-one conversion that we had over here with the volume of water to a mass of water. So this is 0.119 liters, the total liquid is equal to the original 0.75 liters plus that melted ice. So what is this, 0.94 liters there for the amount of liquid of that final meal.
So because there was the phase change, you had to pick what the sign was for that
Yeah.
cube.
And if we forgot, because it was a positive Q, then it would have worked out fine. And that's really gonna be more of an issue where you have more than one Q or more than two, because then you'll be adding or subtracting incorrectly. If there's just two and you forgot the sign, if we were freezing that water instead of melting the ice, then it would have turned out where maybe we would have got a negative mass, because we didn't choose the minus sign up here, and then you might have caught your mistake. But if there were more than two Q's there, you actually would have had the wrong number, not just the wrong sign. And so, yeah, with those Q's, we should always be thinking about which way we're going here. This is positive Q going in that direction. Because we had to add energy to the ice to melt it. And that was coming from the warmer water. If we were going the other way, then we'd have to put that in as a minus sign in the equation up here for those Q's right there.
So if the coldest point wasn't considered 0, is considered 1, then we would have had another Q to calculate, is that correct?
If the coldest was,
Say like
Not 0.
5 degrees
and
Celsius.
if you're warming this up a little bit, and maybe in general, I said, we don't want the coldest tea, but maybe we let it sit there for a while and it actually becomes room temperature or it goes to 5 degrees or something, then yes. If it wasn't the coldest, or if the coldest was 5, then I'd have this Q and another Q right here.
Okay.
And you're gonna do that coming up next on the new class assignment, where I'm gonna give you something with ice that isn't going to be at the coldest possible liquid temperature, and then you're gonna have an additional Q to worry about there. Is that clock right other than the hour? Are we just about at 20 after?
Yeah.
Okay, so we'll go over a lab and I'll give you that in-class assignment. We'll have to start boiling the water, so you'll wait for that, but while you're doing the in-class assignment, you can sit there and wait for your water to boil. So we'll go over there and I'll give you an assignment right there at the beginning. You can take a break though if you want to, start 10 minutes.